All right. Hello, everyone. Hope you're all doing good. And this talk is um, a marketing event, right? So I just want you guys to go out and check out this particular excellent course that I'm following through at the moment. So it's a course by Carl Bender from the Perimeter Archives on mathematical physics. So what is this talk going to be on, right? So in mathematics and in physics, of course, because physics is written in the language of mathematics. So there are some extremely hard problems, right? Um, right. So these extremely hard problems are impossible to arrive. You can't arrive at an analytical solution for these problems. Why is that so? Because you don't know how certain functions behave. How you don't know how to, right? So we will look at one particular problem and we will try to solve it, right? We will try to hit at some kind of a solution, analytical solution, and we will discover new mathematics in the way, and then we'll see where physics comes into picture, right? Because we'll see how the interlinking happens, and yeah, that's that. Then most probably you will just go out and check the video, right? Check the lecture series. So that is the plan for today, to incentivize you guys to go out and check the series by Carl Bender. All right. So now, what are the kinds of problems that we're talking about? I'll start my screen sharing. Yes, here we are. Okay. So the kind of problems that we're talking about are problems like x to the power of 5 plus x is equal to 1. You can't solve this problem. I mean, right now I know your high school brain is running. Oh, you have a polynomial, roots of the polynomial. Okay, factorize, factorize. Factorization doesn't work, right? And also, you don't have a quantic formula, so you can't simplify it into some sort of say split it up into different quadratic equations and solve for the quadratic equation. You can't do that, right? So what do you do now? What's the next step? Well, so in mathematics, you cannot be precise about solution. So I will just do some crazy math first, and then I will just try to see where it all connects, like help you see where it all connects, right? So yeah, so how do you do this problem? You say that the problem that I want to solve is an approximate version of a problem that I can solve. Okay, how do you do that? So you say you insert something called as something like epsilon, which is a very small number in here. Okay. So you insert epsilon before x. So you make the problem that I want to solve into a problem that I probably can solve, right? So which is x to the power of 5 plus epsilon x is equal to 1. Now, okay, right? So what exactly are you doing now? Now you say, take off this epsilon term. I consider the epsilon term as a perturbation, as something that is, extra, that is interfering or that is perturbing my easy problem. So this is a hard problem. This is a very hard problem, an impossible problem. So this is an impossible problem. right? But I want to reduce this impossible problem into a solvable problem where you bring in this epsilon naught. I mean, bring in this epsilon term, and then you make it. You get back the impossible problem. So okay. So what do? You insert an epsilon here. Epsilon is what is just an arbitrary parameter. So we'll see how it works in a bit, right? So now, then you say, oh, okay. So by the way, the analytical solution, like if you do some sort of crazy computing and calculate this up to a million digits or something like that, then you start arriving at an answer that is analytically or that is computationally somewhere this, right? So x is equal to something like 0.755 something, right? So yeah, so that is the approximate solution, like if you can just imagine. So x, so 1, now definitely x has to be smaller than 1, because as the power goes higher, it reduces, so you can't exceed 1. And then you do some mental math, and then you can just reach this solution, right? So now, how do you arrive at this solution in other ways, in a way that is more rigorous? Okay. So what you do is you employ the technique trick that I'm talking to you about, right? So now you have this, and then you say that, hey, my x here, okay. So for the unperturbed problem, so if you have an unperturbed version of the problem, where you can reduce this particular complex problem into a simple one, right? You reduce this into x to the power of 5 is equal to 1. So now what is the solution for this? Very simple. X is equal to 1, right? Easy. So you cannot solve x to the power of 5 plus x is equal to 1. But what you can solve is x to the power of 5 is equal to 1, right? So now, therefore, you get x is equal to 1. And now, okay, using this powerful tool called asymptotic mathematics. So what you do is you say, hey, because I can solve this, I can solve this particular equation and I can perturb it such that I get back this this original equation. All right. So let's say, so this is the original, the unperturbed solution of x. So I'll write it this way, right? Unperturbed plus some terms of epsilon naught. So a n epsilon n, some summation of epsilon from n is equal to 1 to infinity will give you the answer. Or okay, so this is not an equal to here. Equal to is a very, very wrong sign to say, because this, you will never get the answer, right? Because this is an unsolvable problem, so you will never get the answer. So what you say is, as n tends to infinity, this particular series or this particular way of writing down x, okay, will give you is asymptotic to the answer. All right. So what is asymptotic? Asymptotic means tending to. So this particular series, okay, you can write an x unperturbed plus some perturbation term to different or to an order of n, which is tending to which is reaching infinity will give you the answer, right? Will give is asymptotic to the answer, right? So now what you're doing is something very rigorous. You're uh, applying some kind of an approximation, some kind, you're taking limits, and you're saying that, hey, the limits of certain easy problem will give you, I mean, the limits of the solutions of certain easy problem will give you the answer to a very difficult problem. All right. So now, how do you do this? So, right. So you inserted epsilon here, and you inserted epsilon here. So now you solve for x to the power of 5. Then, okay, I'm sorry. Yeah. Okay. Sorry about that. All right. So now you say as n tend to infinity. So you say S is the expansion, right? This particular expansion is S, right? So that is A epsilon. Sorry. Yeah, A epsilon plus B epsilon square plus C epsilon cube plus da 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 da, right? Now you say as as you go higher and higher, okay, you can represent, you can replace x to the power of 5 by 1 plus s to the power of 5, so that, okay, so that you get x to the power of 5 plus x. So you can make, so what you're saying is essentially you're perturbing this x to the power of 5 term to get to x to the power of 5 plus x. So you're perturbing this particular term to get you x, right? So then, okay, so this is one, right? This is the unperturbed x here. So x unperturbed, which we have already found out to be equal to 1, right? So therefore, you have the equation in terms of 1 plus s to the power of 5 is, then you do the binomial expansion of this, which is 1 plus 5s plus 10s square plus da 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 da. Yeah, some other terms, right? I don't want to get into the messy details of it, but yeah, where s is a epsilon plus b epsilon square plus c epsilon cube plus da da da, right? So now what you do is you can solve this, right? You can I mean, you can replace s here for every. So you expand this, and then you get something to the art, something like, okay. So 1 plus 5 a epsilon plus 5 b epsilon square plus 5 c epsilon cube plus something, and then you have the 10 term here, okay, and a square plus 10, and then yeah 10 and then a square, which is something like a square epsilon square, which is the square of the first term, plus 2ab epsilon cube plus so you get some sort of expansion of this. So you're just substituting this in, right? Now, okay. So now comes, so now you can simplify this down to say, you know, 1 plus 5a epsilon plus epsilon square 5b plus 10a square plus epsilon cube terms of 5c plus 20ab plus other term, right? So now, okay, what next? So this term has to be equal to 1. So 1 plus s to the power of 5 is equal to 1. Therefore, you have this whole term. This particular term is equal to 1, right? That means, so now when you solve, so now what do you do? What's the next step, right? The next step is you calculate for the orders of epsilon. That is, you solve for different orders of epsilon. So now, so this is so the for epsilon naught, okay, 1 is equal to 1. All right, very true equation. So yeah, that is the first order, like the unperturbed part of the equation. So that is x unperturbed is equal to 1. That's all you're writing. Now for epsilon square, that is epsilon 2, you have this, okay? 1 plus 5a is equal to 0, okay? Because the perturbation is 0. So therefore, a is equal to minus 1 by 5. Right? Now we go for epsilon cube. Then you have, sorry, epsilon. So this is epsilon 1 and this is epsilon 2. Okay, let me just erase that. Mistake. Yeah, better. Yeah, this is better. Yeah. So epsilon 2 is this particular term, right? This particular term. So you have 5b plus 10a square plus a is equal to 0. Okay. Then you have epsilon. So therefore you have from here you can extract b, right? So this epsilon 1 is a simple equation in terms of a, and then now you know a, then you calculate b, right? Which turns out to be minus, if you calculate this, you get minus 1 by 25, and then you have epsilon cube, which gives you something, and guess what it is, right? Yeah, it is minus 1 by 125. From here on, the series gets more complicated, more complex, and yeah, you basically need to be a very good high school student to be able to solve this series. And I wasn't that good, so yeah, let's leave it at that. Anyway, so once you get this, so you have something to the order of, so once you get this, you have um, 1 minus 1 by 5 minus 1 by 25 minus the other term is equal to the answer. So yeah, of course you have epsilon here, epsilon square and then yeah, so on, right? Yeah. So, so now what you do is you basically insert epsilon into this. So you say that one is the original answer. I think I should probably write this. So, anyways, so you have this solution, right? So you have this solution when you replace epsilon with 1, you get this some sort of expansion, and this is your answer. So which is asymptotic, right? To the actual solution of the problem, the original hard problem that we had, right? So which turns out to be equal to 0.752, which is 3 parts in 750 accurate. Right? That is brilliant. That is absolutely brilliant. What we did with all high school mathematics. Right? First, we inserted the only bold step that we did not do in high school was the insertion of the epsilon. Right? So rest all became extremely easy. Right? So what did we do? We expanded in terms of binomial, the binomial series, and then we inserted epsilon. We inserted the perturbation terms, and then we just expanded, and then we solved for epsilon naught, epsilon one, epsilon square, and so on. Right? So the higher accuracy that you want from the answer, the more orders of epsilon that you calculate. And you can never reach the solution. You can never find out the exact representation of the solution to this particular problem. But you can always go higher and higher in terms of accuracy. All right. So what we did was extremely simple tricks. Using extremely simple steps to reduce this hard problem or impossible problem into a series of easy problems. So you have the so okay. So essentially, what you did here was you reduced this impossible problem into a series. Okay, this is not unequal to again here. This is an asymptotic proof here. So you reduce the impossible problem into a series of easy problems. All you had to do was you had to find the coefficients of a series that looked like this epsilon n a n summation from n is equal to 0 to n. So all you had to do was this particular series, figuring out the sum of this particular series up to different orders of n. Right? So, yes. So now, okay, so the concept, the principle behind this is right. So you have a hard problem, and you break down the hard problem into something that is easy, and as putting certain limits, you say that the hard problem is the easy problem time certain limits. All right. I'm sorry for this. Okay. Yeah, sorry. Yeah, anyways. So you just reduce this hard problem into a series of easy problems. Right? So after that, given this particular technique, so now let's talk about the other where what kind of possible mathematics this all leads to, right? So the first obvious thing is, okay, how can a hard problem tend to an easy problem? Why? Where does this distinguishing, or where does this difference come in, right? So the answer is like, so using epsilon. So when insert epsilon, okay. So where you insert epsilon makes a difference, alright? So now you reduce something highly non-linear into something that is very simple, right? So how does this work? So suppose I'll give you a counter example, and then you can probably extrapolate something. So suppose you had inserted epsilon in before x to the power of 5 term, 5 term here. So you have inserted it here. Okay, this would give you a very divergent answer. Why? Okay, so when you do this, when you insert, yeah, okay. So when you insert epsilon here, saying epsilon x to the power of 5 plus x is equal to 1. So now you obviously have x is equal to 1, which is the unproductive problem. Okay, but here when you see, you're essentially changing the order of the unperturbed problem, right? So you're changing the order of the original problem and the unperturbed problem. So you cannot say that x to the power of 5 is asymptotic to, I mean, x to the power of 5 plus, you cannot say x to the power of 5 plus x is asymptotic to x to the power of, I mean, just x, right? So you cannot say this particular thing. So this is a wrong statement because you have 5 roots here, and you have 5 roots for this complex polynomial here. I mean, and you have 1 root here. So where did the remaining 4 roots go? You must account for that somehow, right? So this becomes a kind of messy statement to deal with. It's not like you can never say this is asymptotic to x, but it becomes much more difficult, right? You're reducing the order of the equation, you're reducing the power of the equation into this thing. You're just swallowing up 4 whole roots, and that becomes problematic. So your curve, obviously, so if you have some kind of polynomial, okay, you're saying this polynomial is asymptotic to a straight line at some point, right? So, right. So for this reason, it might be asymptotic, but then you need to be very, very careful about where you're defining this asymptotic relation. So this asymptotic relation does not hold true whenever the roots, or whenever the zeros of this equation is considered, right? So this becomes a kind of problematic and messy statement made, and you have divergence. I mean divergence. So this study of how a system can get linear and non-linear, how the transition happens, and is where like the bigger part of perturbation theory lies, right? Like the more mathematical parts of perturbation theory lies. So if you guys are interested in that, like that is definitely something you should look up. However, so yeah, so you can approximate this same method. Okay, you can apply the same kind of method to differential equations as well, right? So, for example, if you have y double dash plus q of x y is equal to 0, this again becomes an impossible problem. However, what you can do here is you can insert an epsilon into here and say that y naught double dash is equal to 0, gives the unperturbed problem, and this is very easy to solve. So y naught is equal to ax plus b, which is the first, which is the linear equation, the differentiation, the double differentiate this particular equation with respect to x and you get 0, right? So this is a linear equation, so very easy solution. Now what you do is just say that y of x, the actual y, the perturbed equation or the original differential equation that you want to solve, so, which is this, is now some summation of an of x epsilon from n equal to 0 to infinity, right? So you expand this solution, then it only becomes a matter of saying epsilon naught. Okay, you have this particular relation, right? I mean, you have the solution for y naught here. So now then you solve for epsilon 1, epsilon 2, and so on. Very simple. So you're just solving multiple simple differential equations, not even differential equations, right? You're just solving multiple equations to get this, right? So what you're essentially making again is the statement that by having this unperturbed equation, I can express this unperturbed equation as a summation series in such a way that this particular thing, okay, tends to uh, this the original equation, right? It is perturbed to the original question problem that you have, right? So now, so leaving the math aside, so okay, so what was this equation? This equation was the equation for the nonlinear wave, right? In physics, right? So in physics, the form of nonlinear waves is, I mean, the differential equation looks something like this. All right. So now let's talk about natural physics, right? A little bit. So let's look at this Schrodinger's equation, which nobody has a solution to, right? So I mean, so the Schrodinger equation is something that looks like this, right? Uh, d minus d square by dx square plus v of x, okay, and the wave function is equal to the energy eigenvalues of the wave function, right? So how do you solve this particular equation? So we know the solution only when v of x is x squared by 4, which gives you the simple harmonic oscillator, which is basically the solution in terms of sine and cos wave. So you have then you have energy n is equal to n plus half, right? Where yeah, h bar is equal to 1. So this is the Planck scale. You're dealing at the Planck scale. So your En looks something like this. This is basically the quantized solutions of the simple harmonic oscillator. However, the real problem that we need to solve is not this, not the simple one. So we don't need to solve um, Okay, we don't need to solve this particular equation most often. Okay, we need to like add an extra term here that is to the order of x power 4. So plus g, I mean, yeah, g x to the power of 4 by 4. So how do you do this particular differential equation? How do you solve this equation? Perturbation theory. We just use the exact same method that we used before. So you insert epsilon. So yeah, I'll just write it down again. So minus d square by dx square plus x to the power 4 by 4 plus lambda or g or whatever you want, right? I just prefer writing lambda here. Okay. So lambda x to the power 4 by 4. Okay, the denominators don't really matter, but anyways, phi of x is equal to the eigenvalues of energy, phi of x. Okay, so now what you do is you insert your epsilon into this here, and you say that the x4 term is called as a perturbation term. So it is perturbing the simple harmonic oscillator or the simple solutions to the Schrodinger equation that we already know is being perturbed to include this x to the power 4 term, right? That's what this basically means. So with this, right, you solve Schrodinger equation. So you have tunneling, you have all the different solutions for various potentials using perturbation theory. And perturbation theory helps you, I mean, like it's a whole new field, really. All right. So, in math, so when you are dealing with equal to systems in mathematics, so you say A is equal to B, you can't analyze how you can say, okay, you can say I'll change A a little bit, and I can see how B changes accordingly. But you can't really say that, hey, this is also, I mean, tending to something else with the equal to sign, right? That restricts our mathematics a lot. So you can say that this A is asymptotic to some other term, C, at certain limits. Okay, limits something at some limit. Okay, so right, when you can make statements like this, we can solve problem like 1 plus x. I mean, we can solve problems like this. Sorry, my screen is lagging a lot, but yeah. So when you can make statements like asymptotic to, you can solve problems like x to the power of 5 plus x is equal to 1. And that means that you can also solve problems like differential equation, nonlinear differential equation, which means that you can solve, approximately solve, right? You can get some answer out of the Schrodinger equation. You can get answers out of the quantum field theory equation. So that is essentially the summary of the talk, right? So I mean the uh, beginning of a hopefully long journey for you guys. Um, all right, so we know, yeah, again, definitely do check out the video of Carl Bender. I'll be attaching the link below. And yeah, so Right. So yeah, that's it. Like, I mean, hope this gives you some serious insights, right? Like there are a whole lot of things that I talked about, right? So I just talked about mainly converting impossible problems into a series of solvable problem, very easy problem. And then I also talked to you about a little bit about the thing of solvable, like how the transition happens, right? Where does the solvable problem become impossible? How does this particular transition happen? And there's a very detailed study of that involves a lot of crazy concepts in mathematics, like um, the zeta function and things like that, right? So you have complex spaces and you have a mix of a bunch of topics to a bunch of like tools and areas that are used to analyze nonlinearities. So yeah, I mean, hope you had a you enjoyed the talk, and yes, keep watching the space. Hopefully, something new comes out very soon. Yeah, see you. Bye.